Okay, in this tutorial, we'll be going over element symbols, isotope abundance, and so which is actually how they calculate molar masses. So it's based on the number of isotopes present, and then we'll go into percent composition, and lastly, empirical and molecular formulas, with one example at the end using Dalton's law of definite proportions. So um, this is kind of like the primer slide, is to go over what an element symbol is before we do anything else. So this is an element symbol, and X is again, it's I've used X before, but X is a generic to mean any element. So don't actually write X if you're asked to write an element symbol. You're supposed to write the actual chemical symbol for whatever element it is, and you could usually tell what element it is by looking at Z, which is the proton number. So X is generic for any element. A is the mass number. So you get the mass number by adding protons plus the number of neutrons. This is kind of like my shorthand symbol for a proton. It's a P with a plus symbol. And my shorthand for a neutron is an N with a 0, meaning no charge. So the mass number is everything in the middle of the atom. So around the atom you have like electrons. And in the middle you're going to have protons and neutrons. Draw more circles here. So the mass is given by all of the nucleus. What's in the nucleus? All this is general chem stuff. Z, so how you get what X is actually by looking at Z. So the number of protons is how you identify the element. When that changes, you have a brand new element. So Z is it's referred to as the atomic number, or the number of protons. And this number up here is the charge, and you get this number by taking the difference between the protons and electrons. So if you have more electrons than protons, you're going to have an anion, and if you have more protons than electrons, then you're going to have a cation. So you just take this, you just take the number of protons and you subtract the number of electrons, and you get the charge. Okay, so let me do one quick practice one. Get the charge. Okay, so I'll do it up here. There's some space up here. So if I have protons, if I have 53 protons, if I have 73 neutrons, and electrons if I have 54 of those, and the question is write the element symbol. The element, if you use your periodic table and you look up element number 53, it's iodine. Okay, so it would be iodine. It would be 53 protons. To get the mass number, you would add protons and neutrons, so that would be 126. And for the charge, it would be protons minus electrons, so that would be 53 minus 54, or -1, or -1. So now you guys try this question. So I'll give you, it's exactly the same, and follow this, what I have here, and you should be able to get this correct. So follow these. Let's make that a different color. So use this. Okay, so here's the example. So try that. Write your answer here, and we'll see what you got tomorrow in class. Okay, so just backtracking. So where did we get to this model of the atom? How did we know the nucleus is protons and neutrons, and it's in the middle, and then you have these negative particles whizzing around on the outside? So how did it come to this? So a lot of early scientists were English, and I guess in England they ate something called plum pudding, which is this mixture of like nuts and raisins and pudding and other I don't know, gross things. So they ate plum pudding, and it's all this mixed together stuff. And so they thought the early idea of the atom was they had some notion that there was a positive charge, and but they thought it was just all like smashed together with like some type of goo holding it together, like some type of pudding. So Ernest Rutherford, who was actually from New Zealand, but I'm not sure of his life story, but I believe he was a immigrated to England, where he did most of his early work on the atom. So they thought that it was like this cloud type thing. They thought that everything, all the electrons and protons, were all like stuck together. So anyway, so here's his gold foil experiment. So this is a little bit after he determined radioactive particles. So the same guy, Ernest Rutherford, did some experiments determining alpha, beta, and gamma radiation. So he found out that alpha radiation, which is this is the Greek letter alpha. He found out that the alpha radiation carried a positive charge, and so they proposed that some parts of the nucleus were positive. So they wanted to see what would happen if they shot these alpha beams at a gold foil. The reason they used gold is because gold is really low on the periodic table, meaning it's really dense. So it has a lot of protons and a lot of neutrons. So they wanted to use something that was really dense to try to see if what would happen if these were going to smack into any potential nucleus. So here's what they were expecting to see if the atom was plum pudding. So they actually expected the alpha beams to pass right through the gold foil unobstructed. So to them, the gold foil would have been like a paper towel, and the alpha beams are like bullets. And so logically, if you shoot a bullet at a paper towel, it should go pass right through. I mean, obviously. So they couldn't see any of these beams here. So they couldn't see any of these beams here. So they used a photographic film to try to detect where these alpha beams would end up. So they expected them to all land, or they expected like detection right here, okay, on the film paper. So that's what they were expecting to see if it were plum pudding. So, and if we zoom in on the gold foil, we'll change slides here, and so this is like a zoomed in picture of the gold foil. This is what they were expecting to see, that all the material here wouldn't be big and dense enough to stop the alpha beams. So they figured that it just wasn't dense enough, and the alpha beams would just pass right through. Okay, and detection would show up right here on the photographic film. Okay, so that's what was expected. So what did they actually see? So here's what actually happened: is the alpha beams, some of them, like a small percentage of them, actually hit the gold foil and reflected back, and they picked up detection right here on the film paper. So it would expose the film paper, and I just realized maybe you guys don't even know what film paper is. But a long time ago, before digital photography, they used to have film. So, and then when it's exposed to light, like light will pass over an image, and then the image will block most of the light, and then the film paper picks up on the light that passed through. Anyway, maybe that needs another tutorial. So that's what they actually saw, and this was shocking. This was like shooting the bullet at a paper towel, and the bullet actually bounced, was deflected by the paper towel. So this is really like mind blowing to the early 20th century early atom scientists, like guys like Max Planck, Ernest Rutherford, and Heisenberg, all these early atom scientists. So beams were being deflected backwards. So here's what Rutherford proposed. He proposed that these were, the ones bouncing back must have been hitting something really, really, really dense, much denser than what they were expecting. And so he proposed that electrons were actually separate from the nucleus. And since very few of these actually deflected back, it must mean that a lot of the atom, these beams right here, it meant that a lot of the atom was empty space, which is a little bit spooky since all of physical reality is made of these things. So, and the other outcome, so this is one outcome. The other outcome of the gold foil experiment was that the atom has a very dense nucleus, made of, and they went backwards, which made them believe that the protons had a positive charge. Okay, since they went backwards, I didn't finish my other thought here. So the atom was very, very dense and made of positively charged protons. So two kind of like radical outcomes here from the gold foil experiment. And this was further refined. We'll be going into this in our atomic structure unit, but this is a pretty important experiment, one that comes up a lot in college chemistry classes, the gold foil experiment. So electrons don't, the electrons don't whiz around like what was just animated there. This has been more refined. And it's proposed that they move in like the S and P and D and F orbital shapes. So that because they exhibit like this wave-like behavior because they're moving so fast and they're so tiny, electrons. But anyway, separate empty space. There's lots of distance between, and then a dense nucleus. Okay, so I think this is a topic more appropriate for our atomic structure. This is actually his alpha scattering, or his radiation scattering experiment. But he used a radioactive substance. Rutherford also did. This is a separate experiment than the gold foil one. It went through this little pinhole to try to confine this beam of radioactivity, and he had a charged plate here. One was positive, and so part of the beam went upwards, meaning it was attracted to the positive plate. So the outcome for that beam is he proposed that beta radiation carried a negative charge. Some of these rays pass right through, and they called this gamma radiation. So there's no charge on gamma, and then some of the radiation actually bent and was attracted because it bent towards the negative plate, and so they proposed that alpha radiation had a positive charge. Okay, so this relates because we'll be going into like isotope abundance on the next slide. So okay, so isotope abundance I think we could cover this one as a warm up in class, but let me show you a grade analogy. So if you have a class that uses weighted grades, let's say on the first grading period, second grading period, you get the following grades, third grading period, and then the final. And let's say the weights used are let's say the final is 10%, then we would need 90% for the remaining 3, so divide that by 3. So let's say first grading period is 30%, this is 30%, this is 30%, and let's say you got a 92%, so let's say you have a class, this doesn't happen in my class, by the way, but let's say you got a 92% first grading period, and in the second grading period you got an 89%. And notice we're only using 2 sig figs. So third grading period, let's say you got a 91%, and then on the final, let's say you got an 87% on the final. So here's how you would calculate a weighted average: is you multiply all these numbers here, 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 and then you get these subtotals, and then you add these numbers together, and then that's what's called a weighted average. So it's different than a regular average. I'm sure it has a more technical name, but if you add this, 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 and this, and divide by 4, that's like a regular type of average. A weighted average is different, is you use these category weights. So the way they do calculate molar masses is exactly like this example, 100% the same. So this would actually be if you let's see. So let's say we take 92 times and change these to fractions, 0.3 plus 89 times 0.3 plus 91 times 0.3, and then the final 87. So you didn't notice, like, whatever student this is didn't do as well as they normally do on the final, but the final is only 10%. So that may or may not make a difference. So I put this all in the calculator in one shot, and then you hit enter, and then the overall grade is a 90.3%. I'm kind of breaking some sig fig rules here, but let's say it's grade is 90. I forgot what I got. 90.3. Okay, so 90.3%. If you add this number, this number. Okay, and we'll do I think we'll just do an example as in a warm up following day. Okay, so percent composition. I mean, here's a formula, but I think instead of trying to memorize some formula, just think of a percentage. Just look at what this means. Percent composition. So here's the molecular formula for caffeine, and this says find the percent mass of carbon and hydrogen. So if you get the molar mass of this whole compound, and then you get the molar mass of each individual atom, you'll have the percent of each type of atom. Okay, so for carbon, this would be 8 times the molar mass of 1 carbon, okay, divided by the molar mass of caffeine. I like to use I like to use a if I could find it. Okay, I like to use a calculator. And then you could just type in the formula. So caffeine is C8H10. Okay, C8. It might even be faster just to do this the regular way. O2. Alright, so here we go, finally. So 194.19. 194.19. Oh, it looks like I have all this already typed up. Okay, so, and then times it by 100 to get a percentage. Okay. And I could show you guys an app that's on Apple or Android that does this for you. You just type in the formula and it just spits it out, the mass percentages. It's pretty straightforward, and I don't really think you need tons of practice on doing something like that. Okay, so empirical and molecular formulas. So here's a empirical formula. It's the smallest whole number formula of a chemical formula. So for example, glucose, here's the actual molecular formula of glucose. The empirical formula is this. So 6 goes into 6 once, it goes into 12 twice, and it goes into, so you find like the lowest common denominator that the numbers have all in common. And then you reduce all the subscripts, and that's how you get the empirical formula. Okay, so one last example problem, how to get a molecular formula from percent composition. So here's some steps on how to do this, and we'll get several practice ones in class, so I'm not expecting you to know this exactly immediately right away. So first of all, if you're given percent compositions, assume you have 100 grams. And then convert each element to moles. Divide all the mole amounts by the smallest number of moles present, and we'll see, I think that'll make more sense when we do the example. And this is based on Dalton's law of definite proportions. Okay, you should get whole number ratios when you do step 2, or you should end up with whole numbers for your result here. If you don't, something's wrong. Okay, because atoms don't combine in compounds in like 0.5. Like you have H2O, you don't have H1.50. So you'll never see fractions on molecular formulas. So to get the true formula, you take the actual molar mass, and then you divide it by the molar mass of the empirical formula, and then you should wind up with this whole number integer, and then you multiply the empirical formula by that number. Yeah, I think this will make more sense when we do an example. So here's the example. We have a drug used to treat anxiety. These are the amounts. Okay. What's the empirical formula of diazepam? If the molar mass is this, what's the true formula? So you're given percentages, like in the steps on the previous slide said, assume you have grams. Assume you have 100 grams. since in percent, when you're working with percentages, it should add up to 100%. So assume you have 100 grams of each of those. So for carbon, you're gonna assume you have 67.49 grams, and then change that number to moles of carbon. Okay, and then do the same for each element that you have. So I changed the percentages to masses here, and then I just used the molar mass, okay, of each one to get it to moles. Next, you find the lowest mole number, which is the chlorine atoms here. So your next thing to do, or actually this is a tie between chlorine and oxygen. Okay, and so pick 0.351 and then divide, this is step 2, divide each of these by 0.351, and you should wind up with whole numbers here. Okay, if you don't, something might be wrong. Okay, you might actually wind up with like 0.333 or 0.5, and I'll show you what to do if you wind up with that. But most of the time you should wind up with whole numbers here, or else it's not, the molecule is not following Dalton's law of definite proportions. Okay, because atoms will not be combining in like fraction numbers. Okay, so that is your empirical formula. Is actually, let me write this out. So your empirical formula would be this. Your empirical formula would be C16, H13, N2ClO, Cl1, because there's one chlorine and one oxygen. Okay, so I wrote this out. Use the molar mass calculator online or use the app. I'll show you guys what app to use tomorrow in class. There's one that I prefer. There's like several, but I found bugs with some of the other ones. But so you type this into your app, and then you'll get, this is actually the remember, this is actually the empirical formula, and the question was to get the true formula for this anxiety drug. Okay, and so use the formula from a couple slides ago. This is the empirical formula. So that number, that 284.7, is this number. Okay, and the other number was given to you in the problem. So if I go back to the problem, it's right here. Okay, they give you the molar mass of the actual formula. Okay. So if you divide those two, you should again wind up with a whole number here. And this is actually the lowest common number. So what you do is you take the empirical formula, and then you distribute this 2 and multiply each one of these numbers. Okay, each one of the subscripts, and then you wind up with this. Okay, and then this is your, answer. Okay, this is the true formula. It's a big compound. Most organic molecules and pharmaceutical drugs, and they're like really huge organic molecules. So that's not unusual. Okay. Well, like I said, we'll get more practice with this in class too.